Well, I'll suggest that we get started here. You may not know it, but you're in fact at 3 events simultaneously. So you are in some quantum state that perhaps we can think about it as a university. You're at the internal seminar series for civil and environmental engineering. This is a Geo-Institute event. If anybody is here and in need of PDHs, I have PDHs for you. And I'll end with Osterberg Lecture. First and foremost, it's the Osterberg Lecture, but we're running these 3 events simultaneously. First, a word about the Osterberg Lecture. This is named in honor of George Osterberg, one of the true pioneers of geotechnical engineering. It's an endowed lecture in memorial to Professor Osterberg's lifelong contributions to geotechnical engineering, including innovations in the design and testing of deep foundations. Professor Osterberg was long recognized and is still recognized for his innovations in soil sampling and testing, for 2 inventions in particular, the Osterberg sampler and the Osterberg cell. He enjoyed a long and distinguished career as a professor of civil and engineering here at Northwestern, and as a highly respected teacher and consultant. So we're grateful to the former students and postdocs of George Osterberg who created this endowed lecture. Without further ado, I'm going to keep this introduction short and sweet at Professor Bray's request. It's an absolute pleasure to have a West Coast flavor today here in Chicago. So we welcome this in the Geo-Institute and certainly welcome it here to Northwestern. Professor Bray is the faculty chair in Earthquake Engineering Excellence at UC Berkeley. He is a registered professional engineer, distinction of interest to a lot of our Geo-Institute people. I think what the Geo-Institute people view as the credential of importance. And he has more than 350 research publications. He's a member of the U.S. National Academy of Engineering and has received the Terzaghi Award, Ishihara Lecture, Peck Award, and Joyner Lecture, among many other distinctions. And what you're going to be hearing today is, in fact, a flavor of the Ishihara Lecture with new content. So I will step off and let's bring Professor Bray up here. Thank you for coming.
Thank you. It really is an honor to give the Osterberg Lecture. In the work I'm talking about today, I'll talk about using the Dames and Moore hydraulic piston sampler, which is an Osterberg type sampler. We say that words all the time. And in fact, I tell my students that is really, there's a Laval sampler and a few other fancier ones, but that is the go-to device in terms of sampling soft to medium stiff clays. And then I do peer review on foundations in San Francisco, and not one of them has been done without the Osterberg cell being a key element to understanding the load transfer mechanism of that pile or that drilled shaft system. So it really is an honor to come here to Northwestern, a place that has done such great work. He and his students over the years, thank you very much for inviting me for this. And I'm going to talk about the estimating liquefaction-induced building settlement. And this is, as he mentioned, part of what I talked about in the Ishihara Lecture, and then brings in some new stuff. The principal work was done by Jorge Macedo, and he's now a professor at Georgia Tech, so you're going to see flavor of what he's working on, but there's still things to work on in this area. I've been working on this or trying to make contributions in this area for about a couple of decades, and it really builds on work by other people like Roberto Luque, and Shadid Ashti, Mishko Chubanovsky, and Chris Markham, and others. And so it's always a journey when you decide to take on something. Of course, it requires sponsorships such as the National Science Foundation, the Pacific Earthquake Engineering Research Center, as well as the New Zealand people who've worked with us. Liquefaction, in terms of whether it triggered or not, has actually been a controversial topic. What are the different liquefaction triggering procedures? The way we typically talk about liquefaction is manifestations such as what you see here with a sand boil. It's not a new topic. It was observed in 1906 from the San Francisco earthquake, and it's been observed since then. It really were the 64 Alaskan earthquake and the 64 Nagata earthquake that really we started applying science to it. And you never forget your first kiss or your first sand boil. This is the first sand boil that I physically saw. This is actually, I was part of a team with Professor Ross Boulanger. We were both young students at the time, running around looking at these things. And this is a large sand boil that actually, from the fill that liquefied on the approach to the Bay Bridge, this is 30 centimeters for scale. But what we've lost track of sometimes when we've talked about these controversies of whether liquefaction is triggered or not is what really matters to you as an engineer is the effects of liquefaction, such as these buildings that tipped over as a result of liquefaction in their foundation in 1964, as well as this lateral spreading which affected the bridges. If we focus on the effects of liquefaction, then some of these controversies about triggering curves are less important. It's one thing when liquefaction takes your ride. It's another thing when it takes your throne. But, after going to Christchurch, on a serious note, I thought back of going to New Orleans after Katrina. And the thing that you could not get out of your brain even today is looking at the water line that you saw from the flooding areas in the lower North Ward and other locations. Liquefaction is not just a softening and a failure effect, it's a flood effect. You can see the water stain. People who had moved back into their homes because they were slightly damaged by the September 2010 Darfield earthquake, when they celebrated their holiday season and then basically kissed their Valentine, then all of a sudden they had the 22nd February 2011 earthquake. And it was a liquefaction flood event that caused tremendous damage to the infrastructure. When we look at liquefaction, there's a lot of things you can look at. I like to look at QP plots and pore pressures, and those are key fundamental things. But in terms of consequences, what's most important is shear strain. And this is numbers of cycles of loading. So these are cyclic simple shear tests performed on specimens where you can see the material is basically being loaded back and forth, and there's not much accumulation of strain. And then all of a sudden something happens and leads to this large strain type of phenomenon. If I have a denser material and I put on enough demand, I can incrementally soften and it stiffens, and I softens and it stiffens, and I can accumulate deformation, but it's not the same thing. I think, the late Professor Harry Seed, I took his class at Berkeley, and he always talked about cyclic mobility with unlimited strain potential and cyclic mobility with limited strain potential. And those get too wordy, so we typically talk about liquefaction. But I think we should go back, and I want to be more dramatic. I want to say flow liquefaction. This is very different than cyclic mobility with limited strain potential. This is not necessarily going to flow, but it has the potential to flow. It is a strain softening, brittle, large strain kind of phenomenon. Something we should be very careful and nervous about. Cyclic mobility, if we have a soil that's dense, it can develop pore pressures, and then it can start to dilate and arrest those pore pressures, and it can accumulate strain, but it's a limited strain approach. And so when I look at a liquefaction triggering curve, and so one of the ways, in fact, this is a big contribution from the late Professor Harry Seed, was to look at cyclic stress ratio. So that's an index of the demand, the cyclic stresses induced by the earthquake. And then we look at something that represents the resistance and penetration resistance. In this case, the CPT is that resistance. And the break line between those combinations of cyclic stress ratio or demand and penetration resistances that cause liquefaction. We see liquefaction manifested at the ground surface versus those case histories that have no liquefaction. That dividing line is called the cyclic resistance ratio. And we calculate a factor of safety as being our resistance, or capacity, divided by our demand. Doing so, if I had actually a demand here, and that's my resistance, or I had a demand in this region, and that was my resistance, I would calculate the same factor of safety of 1.2. It's unfortunate that we do it this way because I always like to look at triggering with the backdrop of strains. This means if my factor of safety is not 1.2, because I have uncertainty in my penetration resistance, I have uncertainty in my demand, and I just happen to have the factor of safety approach 1, I go from essentially less than 1% shear strains to large shear strains, probably 20% or more. I'm falling off a cliff. Whereas I'm in this area, if I am off in my demand and it's actually up here instead of down here, I go from 1% to 3% strain. Maybe I go to 5% or 10%. There are consequences to increasing strain, but it's not falling off a cliff. And so I look at this region differently. Even though it's a liquefaction triggering curve, I look at this as being flow liquefaction potential and something I should be very careful about. And maybe a factor of safety 1.2 is not adequate in this region. And then I look at this area over here as being a deformation-based issue where it's cyclic mobility and it's not going to lead to that brittle strain softening. And the break line is around 15 blows for those with the SPT or about 85 for the CPT. Professor Ishihara, which this lecture originally was focused on, the Ishihara lecture, he was one of the first people to look at the effects of liquefaction. And two of his most famous plots are looking at whether I'm going to have manifestations of liquefaction. Because if I have manifestations of liquefaction, then I probably have major issues. And so he looked at several case histories, and he just looked at the thickness of the liquefiable layer, which is shown here in purple, and then the thickness of the layer that is non-liquefiable, which is shown here in yellow. If I have a thin crust and a thick liquefiable layer and the ground shaking is around 0.2 G, this separates those areas with liquefaction-induced ground damage from those without. And of course, there is a function of the intensity or the ground motion demand. But that's an important part of understanding the effects of liquefaction. Another thing is he had a student do some very good cyclic triaxial tests, and then he did post-liquefaction reconsolidation settlement. And then importantly, he put it in a graph form that engineers can use. Engineers can calculate the factor of safety against liquefaction triggering, so that's on the y-axis. And then you can estimate the amount of post-liquefaction volumetric strain as a consequence of liquefaction based on that factor of safety and the relative density. If I have the same factor of safety, but the soil has a lower relative density, then I actually get more volumetric strain. So it's not just the factor of safety, it's the relative density of the soil that combine to give you volumetric strain. My journey in this area started actually in Adapazarı, Turkey in 1999. I'd say 90% of the research that I'm proud of started in the field. I saw something I didn't understand. That's a big reason why I created GEAR, the Geotechnical Extreme Events Reconnaissance, is because you go to the field and you get surprised. There hasn't been an earthquake that I've gone to where I wasn't surprised. In fact, I learned that quickly because in 1995 when I went to the Kobe earthquake, I was amazed how surprised I was. But then I looked around, I saw Professor Idris, I saw Professor Mitchell, I saw Liam Finn, Tom O'Rourke, and they were all surprised. And I realized, if I get into this field, I'm going to be surprised the rest of my career because it will constantly be new things coming up in earthquake engineering. Here we had buildings that had tipped over, buildings that had punched into the liquefied material, buildings that had slid. And a city of about 200,000 people, a quarter of the building stock was so heavily damaged that it had to be taken down as a result of that earthquake. And unfortunately, thousands of people died. Then we have Christchurch, just about 12 years later, and we have, with more modern US-type construction, we have buildings that are sliding 15 centimeters laterally on liquefied material. We have materials that are punched in. Because they didn't want to drive deep foundations into the Rickerton gravel because they have artesian pressures, they had a lot of taller buildings on shallow foundations. They didn't recognize the liquefaction hazard, and now you have tilted buildings. Structural engineers often talk about liquefaction being bad for buildings. Buildings are bad for the ground. When I looked at the Kocaeli earthquake in Turkey, there weren't reports of liquefaction by embraces for the 1967 earthquake there, and it was because they had 1 to 2 story houses that were relatively light. When they start building these 4 to 6 story heavy buildings, that's where you had the liquefaction. In fact, I didn't see liquefaction in the open fields in Adapazarı, Turkey in 1999. I saw it where the buildings were. This is a case where I was told, you have to go look at this, John, because they have a building here. I've lost my mouse is slowing down because I guess the video. This building was a hospital that they built so they could have this hospital in operation after the earthquake. It was not in operation because it was the only place in the town that had liquefaction. The light one-story buildings did not produce enough inertia to cause liquefaction. And this centrifuge test, which I've been showing you, you can see how this building, it's a soil structure interaction problem. The building is basically shaking and working itself into the liquefied material. And so the structure and how kind of inertia it puts into the system is a critical element. This is another fine example of the liquefaction phenomenon. This is a tall building that's on drilled piers where it's well below the liquefiable material. So the surveys indicate that this did not settle. The ground around it liquefied and settled about 300 millimeters. That's the post-liquefaction volumetric settlement. What's important for this three-story building, which is on a mat, is that it punched 400 millimeters into the surrounding soil so that it displaced downward a total of 700 millimeters. And so 300 millimeters because the ground went down, but then an additional 400 millimeters because it went down into the ground so that it had settled 700 millimeters. And so the shear component is a critical component to that settlement, and we were not capturing that. So when we look at displacement mechanisms, I like to break things down into three mechanisms. Ground loss due to ejecta. If I've got 15 centimeters of sand underneath my foundation, and now it's on top of the ground, then that obviously is going to lead to settlement. If I have a building that is being supported due to the stiffness of the underground, of the sands underlying its foundation, but then because the pore pressures increase, the effective stress goes down and it softens, then I can have a bearing capacity or a punching kind of failure. If I could run out there during the earthquake with a cone, I'd push that cone, get very, very low tip resistances. And if I use something like the Schmertmann method, I would say that building's going to settle a lot. And then I have what we showed you from that video is this SSI ratcheting, which is one of the more cruel things that the building does to a soil, is it loads it, which builds up the pore pressures, then it puts it into tension. Soils don't like tension, and then it comes back and hits that soil down. So it's a very effective way of working a soil down, working a building down into a soil. And then we have drainage. The minute you have liquefaction, you're going to have differential heads. Water's going to start moving, and so you'll have some partial or localized drainage. When you get liquefaction, you'll get resedimentation, and then once the soil structure is reformed, the water pressures have to dissipate, and so you'll get post-liquefaction consolidation settlement. Those are volumetric deformations. We need to be able to capture the shear and ejecta. What engineers had been doing, and hopefully do not do anymore, is they were using volumetric strain calculations. In fact, largely methods based on Ishihara's work of using factor of safety and relative density to estimate the post-liquefaction volumetric strain, and they would take information and calculate up the volumetric strain in each layer times the thickness of each layer, sum that up and say, well, that's how much the building's going to settle. Absolutely wrong, because that's free field volumetric settlement. That has nothing to do with the shear. It doesn't include the shear-induced deformation. It doesn't include ejecta. Therefore, you can't use that method for building settlement. One of the best case histories is the case histories in Christchurch, the CTUC building, because we were able to measure differential settlement of about 250 millimeters across the building. There was a pipe connecting this building to that building that had been offset 60 millimeters, so we know how much this building punched in next to the two-story building. The two-story building did not punch into the surrounding soil. This did. And so we have a sense of how much differential settlement we have, as well as the punching settlement on this side. And so we're able, also to see ejecta on the south side. There was no ejecta on the north side. So we not only have a measurement of how much this building settled, but we can look at the different components. There was settlement on the south side due to ejecta, not on the north side. There was more shear-induced deformation than on the south side than the north side. And then we're able to estimate the volumetric because there was a pile-supported bridge that did not settle at some distance away, and so we get a rougher estimate of that. So we have a total settlement, but very importantly, we have this broken down by different components. This is one of the cases that once you go there and you collect that data, now the building's gone now, we were able to actually do cone penetration tests, and this is showing the tip resistance on the right-hand side, and then I sub C, a soil behavior type index, an index of how the soil responds to the penetration of the cone into it. So it gives you a sense of whether it's more of a sand-like or clay-like response. And what you see is we actually started the investigation, 5, 7, 10, 6, and we're on a different line. One of the things I love about the cone is while we're in the field, we recognized there was a difference between the ground conditions on the south side and the north side. So let's go ahead and put in an extra cone right down the middle to find out this ground condition, and we see that it's not there. So we have deeper liquefiable soils on the north side. We actually have less liquefiable soils on the south side, but we have this shallow liquefiable soil right under the building foundation. And in fact, looking back at the maps, before Christchurch was developed, a geologist mapped out all of these streams, which then, while they're building the city, they just filled on top of those streams. Those streams are basically loose, clean sands. So when the earthquake occurs, those streams reemerge, okay? So you cannot bury the soil. It will not be denied. We developed a model. We used a 2D flak analysis in these cases. We used the PM4 sand model that was developed at UC Davis. We're really focused on capturing pore pressure, but also the accumulation of shear stress and shear strain, really the accumulation of shear strain. All of this was calibrated by doing field work, such as shear wave velocity measurements and CPT work, but also laboratory testing. So with the Dames and Moore, I shipped my Dames and Moore hydraulic piston sampler, an Osterberg type sampler, over there to get high quality samples. I actually shipped a cyclotriaxial device over there because you don't want to transport these soils to Berkeley and have them get disturbed. So you take Berkeley to Christchurch and work in Christchurch and minimize sample disturbance. And we develop a model that is as complicated as it needs to be, but no more complicated than that. And one of the key things to capture is this buried stream channel of the looser material that's very shallow, as well as the fact that there's deeper liquefiable soils under the north side, less on the south side. Then we can do dynamic analysis, and we're not getting the answer. We're trying to gain insight when we do this analysis. And what we see, for example, this is the soil profile, is in the loose soil, the loose layer here, away from the building, there are some strains that develop. But because of the building and the loading of the building, both the kind of the static loading of the building as well as the SSI ratcheting, there are significantly higher strains, as you might imagine, under that. And that's what's really leading to greater settlement. In fact, the blue is the north side, the red is the south side. You can see the settlement that occurs is calculated by the program in the median case on the north side versus the south side. And so we can look at our estimated or calculated shear-induced settlement. The green is the best estimate of what the shear-induced settlement is, and it captures it very nicely. It is good that we do not match the measurements because this continuum-based approach is not capturing ejecta. So if my analysis got the right answer, it would be wrong. If an analysis doesn't have the mechanism to capture something, then it shouldn't be right. So I admit that, okay, I'm not going to be able to capture the ejecta-induced settlement with my finite difference continuum-based approach. I'm going to have to look at a different way of doing that. Here's another building. I just want to show some of the lessons. This is a taller building that has the key settlement here is SSI ratcheting. And you see that with the settlement curve. The green is the settlement of the interior column down in the middle. What you see is the building settles more on the outside, which was observed during the earthquake. They did a very careful survey, and they got more settlement at the edges of the building than in the middle of the building. And what you see is this SSI ratcheting mechanism. When the east side is going up relative to where it was, the west side's going down. So you can literally see by doing this calculation the mechanism that's governing this kind of response. It's fine that we got calculated results that are consistent with what's measured, but I think more importantly, it's capturing the mechanism and it's providing the insight to allow you what's important for looking at this problem. So key insights. Liquefaction-induced building settlement is caused by ejecta, shear, and volumetric mechanisms. The 1D post-liquefaction reconsolidation settlement procedure only captures volumetric, so therefore it cannot possibly capture building settlement. A nonlinear dynamic SSI analysis can capture it if it's done carefully and done properly. So just do nonlinear effective stress analysis. But it's complicated, and you probably want to have a sense of what the answer is. In fact, you want to know what the answer is before you do the analysis. If you don't know what the answer is, then you make some silly mistake in your analysis. You don't know that you're off from that reality unless you already know what the answer is. And so really, as an engineer, your idea is to have a sense from just using a pencil and paper or just thinking in your head of what the answer is, and then you do the analysis to get a refinement, and importantly, get a sense of what are the results sensitive to and what are the key mechanisms. So to develop a simplified method that gives you an idea of what the answer is before you start to do the complicated analysis, or in substitution for the analysis if it's been calibrated, we had Jorge, essentially, this was his thesis, a big part of his thesis, Jorge Macedo, was to do this nonlinear dynamic SSI effective stress analysis. This is the baseline case with the building that's 12 meters wide, 12 meters high, has a pressure of 80 kPa. We have a crust of 2 meters, a liquefiable layer of 3 meters, and then material below that. And then we vary things. So thickness of the crust, thickness of the liquefiable layer, the relative density of the material, all from 35 to 90%, building width, height, and contact pressure, and then very importantly, ground motions, a range of different ground motions. We had 12 baseline ground motions, and then we had variations of additional ground motions, so that in all, 1,300 analyses were done. So now we can mine that data and see what's important. Number one is, you see, as you'd expect, the shear mechanism is really important, and you can kind of see almost like a bearing capacity failure occurring in this liquefied material, and you see that the strain distribution that develops. Another important thing is this argument of, is it over-focusing on shear strain? How about the volumetric strain that's occurring during the ground shaking? Well, the red lines are the shear-induced strain in that liquefiable layer at the peak of the ground shaking, when we get to the maximum horizontal acceleration, that's the dotted line, and at the end of strong shaking for this one event, which is at 46 seconds, that's the solid line. And contrast that with the blue line, which is the volumetric settlement calculated at the most intense level of shaking and at the end. You can see that during the intense part of shaking, when you get most of your settlement, it's primarily shear, not volumetric, that's contributing to settlement. And even when you get to the very end of strong shaking, it's still largely shear that's controlling it. So it's not a major inconsistency or error to say that it's primarily shear that's governing. I like the Schmertmann approach for calculating static settlement, so I always like to start with existing methods. I thought I might be able to do something like a Schmertmann triangle to look at the vertical strain that's induced in the liquefiable layer and use that to calculate building settlement. But as I should have suspected, it's a lot more complicated than that, because it's a dynamic problem. It's how the waves are propagating up, it's how they're interacting, it's how pore pressures generate at the bottom of the layer versus the top. And so as things vary in terms of thickness of the liquefiable layer, in terms of the ground shaking, it's not going to be as simple as a triangle and using some kind of elastic approach and bringing it over like Schmertmann was able to do for static settlement. And in fact, the ground motion is a key element. This is just one of the ground motions. This is the acceleration time history. These are the water pressures that develop. We get higher water pressures under the building because the building is putting on a higher total stress, so it has a greater capacity. So there is a tendency for water to want to move out from underneath the building, which does cause some volumetric settlement. Then we have, what's most important, is the settlement versus time. When I looked at this looked a lot like how Arius intensity developed. And as I looked at it further with Jorge, we realized this looks a lot like cumulative absolute velocity. There's a term where you take the acceleration time history, you take the absolute value, so everything's positive, and you essentially integrate the area under the acceleration time history as an index of the energy that's being put in by the earthquake. And you can see that the rate at which the cumulative absolute velocity increases is following very closely the settlement. So that's probably a pretty good parameter to use. In addition to cumulative absolute velocity, we can see that settlement increases as that value increases. It's not sufficient. There's biases, and so we had to add in a spectral acceleration at 1 second, which also shows that kind of trend. Then we look at the building. Other people have done work in this area, Tokimatsu, Ricardo Dobry. We had done some centrifuge work. We knew that building contact pressure had to be important. And settlement should increase as the building pressure increases. I'm just showing you the results for the 12 baseline ground motions. Some of them were deliberately very high, intense ground motions. Others were deliberately less intense. So we can see a range. So obviously the ground motion makes a very big impact on how much settlement you get. But if I just look at the trends, you see that things tend to increase, settlement increases to a point. And then I scratched my head and said, how can you get less settlement for a heavier building? That's what I'm calculating, but I don't believe that. Then I went back and looked at some centrifuge tests. One of the centrifuge tests we had done at UC Davis and one of the centrifuge tests done in England showed one test result that both of us thought were anomalies where there was less settlement for a heavier building. And then you realize, oh, if it's a heavy building, then it has a high total stress on it. If the water pressure can't get up high enough, I don't get all of the effective stress lost. And so actually there is a mechanistic reason why you would get less settlement for a heavier building. And so now I believe that this is true, so I'll accept it. Building width matters. As your building gets wider, your settlement goes down, all other things being constant. And of course, relative density. The state of the soil. So we're looking at soils that have a relative density of 35%. It's tough to find soils in the field that have relative densities less than 30%. So 30 to 40% is pretty low relative density. And then we go as high as 90% relative density. And importantly, you see this kind of trend where there isn't as big a difference between 35 and 50%. But as you go to a medium dense sand, then the settlement rapidly decreases. But importantly, even for a relative density of 90%, you'll generate some pore pressures. If you intensely shake it, it will cause some softening. It will cause some settlement. Then there's the thickness of the liquefiable layer. As the layer gets thicker, you get more settlement up to a point. And this has been one of my arguments, is if it was just continuing to go up, then it would be all volumetric. What this is saying is the layer has to get thick enough to accommodate the shear. Once the shear has been accommodated, if you make the layer thicker and thicker, you've gotten your settlement because you're allowed the shear mechanism. So it's the shear mechanism that governs. And in fact, I had used as a practicing engineer this graph that was proposed that estimated building settlement normalized by the thickness of the liquefiable layer. As I did centrifuge tests with Sinead Ashby, which are shown in green, we deliberately did some that were consistent with a thicker layer, but then we deliberately did some with thinner layers, and we saw that no, this normalization is not fundamental. Because if it was fundamental, then all settlement would be volumetric. If you double the thickness of the liquefiable layer, you double the settlement. But because it's not fundamental, this breaks apart when you go to thinner layers. And then there's the thickness of the non-liquefiable crust. As it gets thicker, you get less settlement. In fact, if the layer was thicker and thicker and thicker, you'd eventually get no shear-induced settlement because the liquefiable layer would be down below the area where the shear is induced by the building. So we have relative density, thickness that matter. Now, this is great for centrifuge testing. It's great for simple modeling, but it's tough for an engineer to estimate these things directly. So let's develop an index that allows them to use this in practice. And so this is the idea of a liquefaction building settlement index, or LBS. The cone is the preferred way to attack this problem. The not-so-standard penetration test is not a viable tool. It's not the best tool for getting relative density and characteristics of a sand, okay? In fact, there's a study that was done in Canada where they found the most efficient way of estimating blow count was to take a cone and using a cone correlation to an SPT number to get that value. I don't think you can say anything more damning about the standard penetration test than saying the best way to get SPT numbers is to use a cone with a correlation, okay? The CPT has the standardization. It has the ability to measure the tip resistance as you're pushing this thing continuously. For clean sands and even silty sands that are non-plastic, the cone is the preferred way of going. So we're going to use a cone-based approach. And if you must, because you only have SPT data, you could do that too. But I would prefer you use the cone, just like Schmertman suggested use the cone for sands and for static settlement. Then we have the liquefaction triggering factor of safety. We develop a column where every layer is defined by its relative density estimate, its factor of safety. It has a thickness, and it has a depth to the midpoint. Then we can use the relative density and the factor of safety with that work done by Ishihara and his student, which was then put into graphical or mathematical terms with equations by Zhang et al. And we can look at this as being a shear strain potential. So as the factor of safety gets lower, as the relative density decreases, we have a higher strain potential. So we're using this as an index of strain. And we just integrate that strain. We normalize it by depth because shallow liquefaction is much more dangerous than deeper liquefaction. So we're using a 1/z reciprocal of depth. And then we multiply it by dz. This is just to make sure we don't count values that are above, layers that are above the base of the excavation. You don't have to memorize this or do this because I worked with Peter Robertson and said, you know what, you've got the Zhang et al. Procedure in your program, CLIC. Let's go ahead and put this procedure in, and that way practicing engineers can use it. So it's actually embodied in the relatively popular program, CLIC. I always like to start a problem with a sense of what the answer is. And just like if you're doing an excavation, you calculate the factor of safety against base heave. And if you know that factor of safety is high, you probably are not going to have an issue with excavation-induced movements. That factor of safety gets below 1.5, gets close to 1, then you know you're going to have a lot of problems with, potential problems with excavation-induced settlement. And so why don't we take this two-layer bearing capacity equation that Meyerhoff developed with his student Hannah. Let's look at the crust and the liquefiable layer. Let's give a kind of an average strength of the crust, get a post-liquefaction residual liquefied strength for the liquefied material, and let's calculate a post-liquefaction static bearing capacity factor of safety, just as an index of how bad the problem would be. And it's not a bad index in the sense that if the factor of safety is high, the settlements are going to be relatively low. If the factor of safety is low, for example, less than 1, you have the potential for large settlement. Of course, well, why would you have numbers down here? And there's two reasons why we have numbers down here. One is I'm using a two-layered system, and there are layers that are thin and I'm using a two-layered system. I'd like to find a closed-form three-layer system. So if you have a closed-form three-layer system solution around, let me know, because I'd like to bring that in. That would get rid of that issue. The other case here is this doesn't talk about the fact when you have really heavy buildings suppressing the development of liquefaction. But overall, it's a good index. So the key insights from this part of the study, the shear-induced mechanism governs during ground shaking, ejecta-2 if it occurs. Large building settlements are possible when the factor of safety against bearing capacity failure after liquefaction is less than 1. The key ground motion parameters were found to be cumulative absolute velocity and spectral acceleration at 1 second. The key building parameters are the contact pressure and its width. And the key site parameters are relative density, thickness of the liquefiable layer, thickness of the crust. But you can bring that all in and calculate that with a cone penetration device. In fact, the program CLIC calculates LBS automatically based on your cone data. And so this is the equation we came up with. We're not focusing on all the details. It's obviously the shear-induced deformation is dependent on LBS, that index of the liquefaction settlement. The building contact pressure is a very important parameter. And of course, the ground motion parameters that I talked about. Importantly, we did this in a statistical sense so that given you know all of these numbers, this is the uncertainty in estimating the shear-induced component, and it's significant. It's natural log, so it's e to the 0.5, so that means that if you know all these numbers precisely, the shear-induced settlement is going to be maybe 0.6 to 1.6 times that value. But this is a difficult problem, so anyone who promises you better than that, I would be suspicious. Now I had to hire another postdoc or PhD student and do a whole set of analysis because I had only used PM4 SAN, one constitutive model, in FLAC, one program. There's clearly going to be some bias there. Luckily, my former student Sinead Ashby, working with her PhD students, had decided we're not going to use FLAC. We're going to use OpenSeas. We're not going to use PM4 SAN. We're going to use the pressure-dependent model that Professor Elgamal came up with. And she kindly shared the data, and this is the relationship between the predictions from our method and what they got from their analysis. And the trends are pretty consistent, except when you get to small numbers. But small numbers don't matter to me in a practical sense because to an engineer, 1 millimeter and 4 millimeters, yeah, it's a factor of 4, but they're the same number. They're negligible. So I don't care about that misfit. I care about it over here. And so now I don't have to hire another PhD student and do a bunch of analysis. This works for 2 different effective stress analysis. And then I want to go back to the centrifuge tests, where I measured very carefully what the settlement is. I can now estimate it with the simplified method. And again, within a factor of 2, it's capturing the trends pretty well. But I'm not going to stop there because what started this whole thing were field case histories. So I'm going to take 19 of the best case histories I have where I can look at shear, ejecta, and volumetric displacement, and this is just a subset of those, primarily from the Christchurch earthquake and the Kojali earthquake, but also Darfield and Juneau are in there as well. These are some of the buildings I looked at. This is the observed shear-induced settlement, and this is what we calculate with our simplified method from 16th percentile to 84th percentile. You always want to give a range. And for the most part, when you look at that, they compare favorably. The observed shear-induced settlement is close or within the bounds estimated by the simplified method. And most importantly, like for example, for the same building, you can see that it captures that you're going to have more settlement during the Christchurch earthquake. And yes, there was more settlement for that event. And you're going to have significantly less settlement for the Darfield and June event, which this method captures. I gave this presentation a few years ago, and then one of the professors stood up, Professor Liam Finn, and goes, that's fine. You've got shear-induced settlement. We got volumetric from the existing techniques. What about ejecta? And so this is not an easy problem, but we've got to not ignore it. We have to realize that if I have ejecta on the ground surface, that had to have contributed to the settlement. First, we start off with case histories, and we have something called a liquefaction severity number, which I like because it's a function of volumetric strain. So he's using the Ishihara developed method for estimating volumetric strain as a proxy for the severity of the liquefaction damage. Notice that he normalized that by 1 over z. I was actually part of that team. That's another reason why I still use 1 over z. I think normalizing something by 1 over the depth makes shallow liquefaction that much more important, and our case history suggests it is that important. So this is looking at LSN. First thing we do is we see that thick, clean sand sites, which are a majority of what we focus on in liquefaction in our case histories, have to be dealt with differently than stratified silty soil sites, which are not plentiful in our liquefaction database, and so it's not surprising we don't do as well for those soils. LSN seems to be a reasonable break of about 10, that if you have a low LSN number, you don't have manifestations. If your LS number is greater than 10, you do get manifestations, but you can't differentiate when it's minor, moderate, or severe. So it's of limited use. Same thing for silty soils. There appears to be a break at a higher number because of the bias in our methods at silty soil sites, which we could talk about later, between no ejecta and ejecta. So it can tell us that break line. The fortunate thing is silty soil sites don't tend to have large amounts of ejecta. But let's look at what this, and I apologize for the language, but I wanted you to hear the water flowing. This is somebody who had lived through the Darfield earthquake and saw a little bit of liquefaction. This is their backyard after the Christchurch earthquake. So the shaking has stopped. This video goes on for over 3.5 minutes. This is not a broken water pipe. This is high water pressure that's been generated by the earthquake. And that water now is above hydrostatic. It wants to come out, and it comes out, and you basically have this going on, bringing all of this ejecta to the ground surface. So then you realize the ejecta problem is as much a hydraulics problem, a fluid mechanics problem, as it is a solid mechanics problem. So just thinking about a crust on top of a liquefiable layer below the water table and a denser sand layer that won't liquefy, but it can generate pore pressure. And let's go back to probably something you looked at in your basic soil mechanics class in terms of total head. I'll put the datum at the bottom, and we'll look at elevation head, increasing above the datum. We'll look at the hydrostatic pressure head. And of course, for the hydrostatic case, there is no flow because you add those two together, you basically get constant total head. What the earthquake does is it generates pore pressures. It can be as high as what was the vertical effective stress. And so let's say we have liquefaction at this point. If you put a piezometer in the ground, you'd measure a water pressure at that point, which is in excess of what was the hydrostatic case. And so we can look at that, and we can look at then with time, those pore pressures will dissipate, and this will eventually go back to the hydrostatic case. So let's just look at this excess, which is the total head minus the hydrostatic, as that which then has the ability to generate ejecta. If we just simply take a one-to-one line and say if the excess head is above that one-to-one line, if there was a crack in the ground, then that water would then be artesian, and it would want to come up, and when the water comes up, it brings the soil up with it. A crack will eventually develop. Some cracks might happen during the ground shaking because of differential shaking, but eventually the water pressure will find its way, find a defect. That's why you tend to find ejecta next to telephone poles, next to sewer lines, next to pile-supported buildings, because those are defects through the crust. It brings up the water, but very importantly, that denser sand layer is supplying that water that's keeping it going. So this secondary liquefaction, not due to ground shaking, but just because you have this residual excess pore pressure, is a key thing in terms of driving this mechanism. So we were looking at several different parameters, but one of them is just taking the excess head minus that head that would cause upward flow, squaring it to just emphasize it, times the thickness. So we end up with a volume. That's another reason why I like squaring it. So we end up with meter cubed. So let's look at two sites, 3 earthquakes. The Shirley site is on the top. The St. Teresa site is on the bottom. There was no liquefaction observed for any of the earthquakes at St. Teresa. It's a silty soil site. The Shirley site had none for the Darfield earthquake, was extreme for the Christchurch earthquake, was severe for the June event. The LSN numbers are shown here, and they don't work so well. So again, LSN is an index, but it's not sufficient. So let's do some nonlinear effective stress analysis. Those are some of the details, which I'll skip over. And what we're showing now is the Shirley site. This is the Darfield earthquake, Christchurch earthquake, the June earthquake. This is the displacement profile that's calculated, so you can just see a sense of how things are shaking. But most importantly is looking at the development of pore pressures, and this would be RU equal to 1. So this is what the vertical effective stress was, and then this is above the 1-to-1 line. So let's get this started. And then this is calculating that term, ejecta intensity versus time. So you can see the Christchurch earthquake in the middle is much more severe, intense shaking. It's shorter in duration. In fact, the time history is given on the bottom there. Let me see if I can go forward here. Let's not do that. Maybe not. Well, what you see how the line's coming up here? Right in the middle one. Much of the excess, it's for that bottom part of the water, that SP2 layer is actually supplying water that's coming up and sustaining the liquefaction and the flow of water well past when the ground shaking was occurring. This is St. Teresa, so same kind of plot. What you'll see is there are layers that actually generate high pore pressures or high excess head, but they're isolated. They're disconnected because there's barriers with low hydraulic conductivity between them, and they never basically get to the point where they have sufficient excess head to cross the 1-to-1 line and cause ejecta to occur. And there's none in terms of the ejecta intensity parameter. So looking at these 3 case histories, we have none for Darfield, severe for the Christchurch, for the June event, and extreme for the Christchurch earthquake for the Shirley event, and then for the silty soil site, St. Teresa, it's down on the bottom, it's none for all of them. And so this is giving us a sense of how these sites might generate ejecta. And in fact, this parameter, if I integrate it over time, so I take my ejecta potential and ejecta intensity and integrate it over the time history of shaking and post-shaking, that's a very important part of it, we can see that it does a pretty good job of telling us when we should have a lot of ejecta and when we should have less. It does a better job of discriminating than LSN. So I think we're starting to move in the right direction. So I'd like to finish up quickly by summarizing what we have right now. I think I am proposing a simplified method for estimating liquefaction-induced building settlement. Let's go back to this building that we talked about and apply it. It's defined or delineated in the Soil Dynamics Earthquake Engineering Journal in the Bray and Macedo 2017 paper. So the first thing you do is you do a liquefaction triggered assessment, find out those layers where liquefaction is to be triggered, and that's shown here in red and orange. You do a post-liquefaction bearing capacity factor of safety calculation using the liquefied residual strength. The factor of safety is low, so I anticipate large settlements. The weak link for now is ejecta-induced settlement. It's easy. I have a low LSN, and so I can say there's no ejecta-induced settlement on the north side, and none was observed. I have a higher LSN. I can also use the Ishihara plot I talked about in terms of ground failure. I can use judgment. This is a more precise estimate because I know what the answer is, but this would be a large uncertainty, and we're working on that to try to improve that. Then we look at the volumetrically induced settlement. There is a method based on Ishihara's data that was put together by Peter Robertson and his student. So we just use that volumetrically induced method to get that. And now we have the shear-induced settlement method from Bray and Macedo 2017, and it calculates more settlement on the south side than on the north side, primarily because of the high LBS number you have on the south side, because you have that shallow liquefiable soil right beneath the building. The total settlement is that due to ejecta, volumetric, and shear. And these are the median numbers on the south side, about 480 millimeters, and this is on the north side, about 220 millimeters. Of course, there's uncertainty, so this is the actual range that you report in the report. The estimated differential, of course, differential settlement is most important for building damage, is 260, and the actual amount is 250. Now, two things. Of course, I'm going to show you my best case because I want you to be impressed. And two is, this is no guarantee that you're going to get the same level of accuracy. But the bottom line is, at least you're getting in the ballpark. You now have a method that can look at the different components of settlement and make a rough estimate of what that will be. So in conclusion, I have hopefully convinced you that liquefaction-induced building settlement is an important issue, and it really has three major components: ejecta, shear, and volumetric mechanisms. The shear mechanism, which we had not had a method to capture, governs during earthquake shaking, also ejecta when it happens, and we're working on that. This new procedure I'm proposing, which was presented in the Ishihara lecture paper, allows you to estimate that shear-induced settlement. And you would never use that method unless it's been validated. It's been shown to be consistent with 19 well-documented field case histories, 102 centrifuge test results, and thousands of dynamic analysis, not just the 1,000 that we did, but the tens of thousands that Sinead Ashty did independently. Thank you.
Thank you, John. This was a wonderful lecture that spanned fundamentals all the way to practice, and I think it's an inspiration to us all. We are going to ask questions if we may. I know that some people potentially have to run because it's noon and we're here in the middle of the day here at Northwestern, so if you do have to run, grab a croissant. If you can stay, we have the room. We're comfortable here for a while, and we can ask a few questions. Would anybody like to start? John.
Microphone. Thanks. That was really interesting. I don't know much about this, but I knew more at the end of your talk than at the beginning, so that's a good thing. I was going to ask where you get your ground motions. Are there typically accelerometers nearby, and isn't that largely dependent on site conditions?
That's a very good point. One of the first things we look at when we have an event is, was it well recorded? The Haiti earthquake's a very important event, but there was no ground motion stations that recorded that event. Christchurch, they had invested in strong motion stations. So there's 29 strong motion stations in the Canterbury region that recorded that ground motion. In the downtown area, there's 4 strong motion stations that give good confidence of what the ground shaking was for all of those events. We also have some nonlinearity, and so we also found a couple of stations at really stiff sites that were much less nonlinear. And so what we do is we take those ground recordings on the sites that were more linear, we deconvolve those down to what the ground motion must have been at the stiff layer beneath all those, And then we bring those over and propagate them up, and then we check them against what was recorded at the nearby stations. So there's not much more important than the input ground motion. So we actually, that's Chris Markham's work. I mean, everything is building a piece of the pie. Chris Markham's thesis, a big part of it was finding those sites, doing the deconvolution, developing ground motions, taking ground motions with this method, and then estimating what they should have been at sites where there were recordings and making sure that we had a good comparison. Only after we had done all of that could then we be bold enough to start doing two-dimensional nonlinear effective stress analysis of a site with a structure on it. If I can't do free field, just normal site response and see how the ground motion varies with different site conditions, then I can't possibly do nonlinear effective stress analysis of a building.
Thanks. Thank you very much for this interesting lecture. I have a question about the ejecta mechanism. Do you have any evidence about any relationship between the significance of ejecta and the shear properties of soils? Because I would expect that since it's, as you said, kind of a fluid mechanics related problem and a penetration related problem, there could be like a relationship between, for example, shear models of the soil or angle of shear strength.
Yeah, and that's one reason why a liquefaction severity number works in a broad sense, because it's relating volumetric strain, and those soils that have higher volumetric strain potential will tend to have more ejecta. A loose, clean sand produces more ejecta than a medium dense sand. So there is that relationship. And it's a difficult problem because one of the hardest things is the crust. And minor defects in the crust, like telephone poles or trenches for water lines being put in, if the crust has any defect in it, that's where a crack happens, and then the water finds that crack and then erodes that crack, and you tend to have a large amount of ejecta over here. And just because you don't have ejecta over here, it's because that ground was strong. Like, let's say there was a concrete pad on top of it, so it can't go out there. And so all of that liquefaction that would have been manifested here comes out laterally and then comes up through this one crack. It's a difficult fluid mechanics problem, and it's something that that we're attacking with some of the analysis we're showing here, but we were doing a lot of field work too, because the great thing about the Christchurch earthquake is they did LiDAR measurements after the earthquake. They also measured the amount of sand that they took away from a lot of the sites. So we have some case histories that are giving us some evidence. And we actually have some people doing laboratory testing to look more at ejecta. So I think there's promise, and I think the key thing is to remember that it is as much a fluid mechanics problem as it is a solid mechanics problem. And it's a challenging one. So I'm never going to be able to say you're going to get 100 millimeters of settlement. I think I'll be successful if I could say no ejecta-induced settlement, maybe 50 to 200 millimeters of ejecta-induced settlement, maybe more than 200. I maybe hopefully be able to put it into 4 or 5 broad categories. And maybe a newer method is like MPM. MPM might be a way of starting to look at this in a more fundamental level. But then you have to think about all the realities of the field. Is you ever going to know where all the water lines are, all the defects are, where the telephone poles, the post, mailbox? I mean, it's a difficult problem.
What's MPM?
The material point method.
Or SPH. We have Tony Dalrymple here. So.
Thank you very much. It was an inspiring lecture, and it was great to see very clearly explained the various contributions for settlement and the relevance of shearing effects. The question I have comes from the fact that the tool that displayed very clearly the relative role of the different contributions was a nonlinear analysis with an advanced constitutive model, where basically volumetric and shear effects are both embedded, they are tightly coupled, so shearing occurs, but pore pressure builds up. And after the event, consolidation and volumetric strains take place. But when you move to simplified approaches where you kind of separate them, you kind of want to keep these feedbacks into the loop. What strategy did you manage to use to make sure that the shearing-induced effects take into account pore pressure build-up and other processes, And the volumetric 1D approach remembers the fact that as volumetric strain develops, also shear strain might pop up in the process.
They are coupled, and in an effort to kind of simplify things so that you can break things apart, what we often do as engineers is we separate things that we know we shouldn't separate. Shade Dashti, my former student, has an entirely different approach. She believes it should all be pulled together and tries to do it all at the same time. But her method can't capture ejecta-induced settlement, and so they have to kind of do a calibration at the end to do that. I've done enough analysis and looked at enough centrifuge tests where I think there's enough evidence to say it's during strong shaking, it's largely shear. It's not 100%, but it's largely shear. And after strong shaking, it's largely volumetric. PM4 sand actually in a lot of models don't do a good job on post-liquefaction volumetric strain. So actually what PM4 sand does is they put like a little flag in there just to get the same answer they would have gotten with a Zhang et al. 2002 volumetric empirical procedure. So we have some work to do with our models to handle that. So I feel like this model could handle shear well. It was developed for looking at earth dams where the shear-induced deformation was dominant. Peter Byrne did the same thing with UBC sand, developing a model that captures the shear-induced deformation, and then his flow rule captured the volumetric not so well. So since the model does well for shear, I feel very comfortable using it to try to capture the shear deformation. And since the centrifuge tests and the analysis suggest it's largely occurring during ground shaking, which principally controlled by shear, I feel comfortable separating them. I think as we get further down the road, a student down the road probably can improve this method by bringing in some of the coupling. Just like Harry Seed and Phase McDC decoupled the site response from their calculation of Newmark block analysis, and now Ellen Rathje and I recoupled those together. I think that day will come, but this is a difficult enough problem. I like breaking it apart in those building blocks. And I'll admit there are some shortcomings to that theoretically.
Thank you.
Whoa. Maybe we're too. Yeah. You observe many buildings. Are there any examples of observing ejecta below floating floor slabs? In other words, are there places where you can go and actually do a lot of field test comparables because you know where the ejecta occurred under the building? I realize that you can go to those sand boils outside the building as well, but the evidence within the building, and that's both with maybe shallow foundations mixed with floating slabs, or maybe, I don't know, it's pretty uncommon to have a floating slab below a pier foundation, but my point is, are there any examples that you've observed that where this complete settlement system, in other words, all three components get to be measured because structurally you've got evidence to look at?
There are a few cases. There was a really nice case in Turkey where there was a two-story building on load-bearing walls that were down on shallow foundations around the side, and it actually had a floating slab that floated up, and there was ejecta everywhere. You could see how it heaved up because of the ejecta coming through. There are other cases of shallow foundations with tie beams connecting them a bit. I'm not a big tie beam person. I like more of a grade beam to really have a nice, good structural connections that show some of this interdependence. A lot of our cases, however, and all the centrifuge tests have been relatively thick mats where the mat has been like what we modeled and what I showed today, where it's a relatively thick mat that there's no breaking of that mat and the ejecta comes out on the outside of it. But there are residential homes and there are some case histories of light buildings that have ejecta coming up. And the Christchurch Town Hall, we actually were able to measure the amount of ejecta that came up through that slab because they actually had to cart it away, and they measured it.
My question, if there are places where this is manifesting itself, have you tried to calibrate the whole system against that?
Yeah, the Christchurch Town Hall is one of the case histories that we do, because we do bring in the amount due to the ejecta settlement from the inside the building, as well as the building settlement due to the weight, the outside weight. So there are fewer of those case histories, and we have included some of those in, and we're able to break things apart by those mechanisms. They're not as simple, so they're more complicated. Yeah. Of course. I know.
Any other questions from the audience? If not, I have one myself, which is you emphasized, and I found that very energizing throughout your talk, that mistakes are made. You really just have to, this is such an open problem that you have to attack it. You made reference to the Ishihara method, which is wrong because it only deals with volumetric deformations and free field motions. So for the students who are sitting here today, who are copious, how acceptable, is it okay to be wrong, and how wrong? And have you ever published a wrong result?
I thought I had made a mistake once, but I was wrong. No, and very importantly, the Ishihara method's not wrong. He came up with a method for doing volumetric. It was us, the engineers, taking that method, and because there were no other methods around, using it incorrectly. And I mean, to me, the whole thing is you're constantly wrong. I tell people in my geotechnical earthquake engineering course, if you ever want to be right, don't take this course. Because what you're doing as an earthquake engineer is you will never be right, you will never be perfect, you just don't want to be wrong. When we have peer review and we're looking at ground motions, we're looking at site response, we can get Ed Idris, John Bray, and Norm Abramson in the room, and we can all agree what's wrong. But we can never agree what is the best, because we all have our personal biases and such. So you'll never be perfect in this field. You'll always be struggling. There'll be some things you do well and some things you do poorly, and you're always working toward things. I mean, this is something I had hoped to solve with Rodolfo Sancio's thesis in 2004. We obviously didn't solve it. And I worked on this many, many times. And so you didn't see all the papers I would have written being wrong. So I do believe in going a little slower and methodically, put something out that takes the step forward, make little steps, maybe you make a step back and you make a step forward. It was the Ishihara lecture. I said, you know what, Jorge, and with all these case histories at Christchurch, I think now's the time we might be able to pull this off. And I think this is a good first attempt. I'll be surprised if you're using my method a decade from now, because I think somebody will come along and find some things, do a few things better, and somebody will be using another method 10 years from now. Just like you shouldn't be using Bray and Travasero anymore. You should be using Bray and Macedo.
I think this is a perfect place to close it on that note. I would like.
I'm wrong?
Thank you so much for coming all this way, John, in the middle of the semester at UC Berkeley. We wish that you could stay longer and we could wine and dine you better, but all good things must come to an end. Your tour is not over here. Some of you will be seeing him later today, but let's end with a big round of applause and thanks for coming here to give this lecture.
Thank you.